Hi, kiddos! Yes, we are talking about Unit 4, your most favorite and least boring unit. We will be talking about Earth's resources and Earth's systems. That means we'll be focusing mostly on the abiotic factors of an ecosystem, things like weather. Pretty exciting stuff. I love this phrase that Earth systems interact, resulting in a state of balance over time, because it is both true and is totally not true at the same time. Earth systems are incredibly complex. The learning objectives for this particular unit were to describe geological changes, to describe characteristics in the formation of soil, which is both an abiotic and a biotic component of our ecosystem, to describe similarities and different properties of different soil types, to describe structures of compositions of Earth's atmosphere, explain how environmental factors can result in atmospheric circulation, describe the characteristics of watersheds, explain how the sun's energy affects the Earth's surface, that causes seasons, try to figure out why geography can impact both weather and climate, and then talk about things like El Nino and La Nina, which are periodic weather events. So first of all, we're going to start off with this geological concept of plate tectonics. Plate tectonics is that our Earth is, the terrestrial Earth is sitting on a bunch of plates that are consistently moving due to fluctuations in the magma in the Earth's mantle. So as that magma circulates, it pushes pressure on these plates that are floating on top of it and can cause them to do minute movements, but then it can cause massive geological events like earthquakes and volcanoes. You do need to know a few key components of the plate tectonic theory. Mainly, you need to know what happens at the different types of boundaries. So at convergent boundaries where two plates are coming together, you're going to have one plate that's going to be sliding underneath one. You're going to find mountains, island arcs, earthquakes, and volcanoes there. At divergent boundaries where two plates are separating, you're going to find seafloor spreading, rift valleys, volcanoes, and earthquakes. And then at transform boundaries where they're just sliding past each other, like that one on the far right, you're just going to have earthquakes. Usually those are not associated with volcanoes. Soil formation is dependent on 5 major things. You can think of them as 6 if you would like. You've got parent material, so what type of material is actually going to be used to form the soil. Topography, so how is that soil going to be transported and then deposited. Time, how much time do all these factors have to accumulate. Climate, which has to do with heat and precipitation, and then the biota that's going to live in that particular area. Those are all things that contribute to soil formation. As you can see to the left, you've got a illustration that talks about soil's character depending on climate. So for instance, you can see here you've got precipitation, you can have infiltration, you have a plant accumulation of debris, worms, biotic factors are going to be churning here. You've got microbes that are going to be doing nutrient cycling. You've got roots that are going to be breaking down material, mineral components of material. You've got this downward percolation of water, which is going to pull with it ions down here. And then oftentimes you'll have some sort of bedrock down here. And this area here will start to accumulate ions, or those ions can be actually leached from the system due to lateral or sideways water flow. If you're looking at a perfect column of soil, there really is no perfect column of soil, but we're going to pretend. So let's say this right here is a perfect column of soil. You would have an accumulation of different horizons over a very long period of time. So you're going to have the O horizon, which you can see observable matter that is organic. So think of observable organics, meaning I can pick up, like maybe it's a dead leaf, but I can see that it's a leaf right here, right? Then under that, you're going to have an A horizon. An A horizon is usually dark with organics. So this right here, this would be A horizon. You know when you buy dirt at like Home Depot, how it's nice and dark? That is this type of soil right here, topsoil. Then after that, you may have a zone of alluviation. Alluviation refers to the fact that sometimes as the water moves through the soil column, with that process called percolation, infiltration goes in, percolation goes through. So as that water moves through the soil column, there can be this area where the nutrients are being pulled downwards and they've actually been almost completely pulled out of the mineral content of the soil. It's called glaying. So anyways, we have that a zone of alluviation, so it goes A, E, and then B is a zone of accumulation, and then you have C, which is weathered bedrock and parent material, okay? So you do need to know A, E, B, C. You also need to know what makes up the O horizon of soils. You need to kind of have an idea of what infiltration is, what percolation is, and that zone of accumulation. So here are some real life soil samples for you. You can see here, this right here I would call the O layer, the O horizon. This right here would be the A. This would be the E. This would be the B. And then you can see that this is probably the C, or I may not be seeing it. It looks like there's a color difference there between these two. So this would be a zone of organics, right? And then this would be the zone of alluviation. This is the zone of accumulation, and then this is probably the bedrock down here. Now, it doesn't always look like that, and that's part of what makes this so hard. Like right here, you can see this looks like an A layer of soil straight on top of bedrock, right? Like the bedrock is right there. So if you have very low soil accumulation, you can have stuff like that. When you are doing the AP exam, they are going to give you a very clear diagram. So I don't want you to stress about it. It's going to show usually all of the soil horizons, and it's going to be very clear. You guys may remember the soil texture triangle. So if you have % clay that goes this side, and that goes across the triangle, you have % silt, which goes down this way, and that is going to go slantways down, and then you have sand, which goes diagonal up. Right? So across, down, up, across, down, up. Okay? And so then you oftentimes in the AP exam, you'll be given something like, oh, it's 60% clay and 20% silt, and they won't even give you sand. It doesn't matter. You have 60% clay, 20% silt. Oh, I'm already right here. I can even tell you how much sand that will leave me. That will leave me exactly 20% sand, right? And you could have also done that by subtracting that from 100%. So soil properties that you need to be aware of are things like soil texture, right, which we can calculate from the soil texture triangle, which talks about how much clay, sand, and silt a soil has, and that could lead to a variety of different physical and chemical properties and even biological properties that a soil will have. So remember, clays are very, very tiny particles, sands are very large particles, and silts are fine particles somewhere in between a sand and a clay. A loamy soil has a tendency to have heavy organics, and oftentimes this is what we associate with like topsoil that you buy at Home Depot. A loamy soil is going to have heavy organics. It's going to absorb a lot of water, and we think of that as the perfect growing soil. But you have to remember the perfect growing soil for what? So if you are growing roses, you want to buy soil for roses. If you are growing a cactus, you don't want to put that in a rose garden. It's not going to do well there. You're going to put that in a more sandy soil. So depending on what you're trying to grow, you need to think about the soil type that's best for that particular agricultural product. Chemical properties in soil can include things like pH, organic matter, how much nutrient availability there are, and even soil pollutants. Physical properties are how easily it aggregates or it clumps together. So if you squeeze it, like, will it stay in that clump? Soil porosity, so how that will influence how water infiltrates and percolates through the soil. Bulk density, how compacted the soil is and how much soil water it can hold. Notice there's a lot about soil water. We'll talk about that later. And then, of course, there's microbial properties. So what is the microfauna and the mesofauna that's living right there within the soil? Something that sometimes trips up my students is the difference between erosion and leaching. So remember this right here, this demonstrates erosion of soil, the physical movement of soil and mineral particles, okay? Whereas leaching is the movement of chemical nutrients and chemical particles from the soil. So leaching is like the water dissolves phosphorus from the soil and then pulls it out of the system as it moves to the stream, whereas erosion is physically moving the whole soil or the particulate parts of the soil from the agricultural land to the stream, okay? That can then be associated with a variety of negative impacts on the stream, like we've talked about, increase in turbidity, which is an increase in sediment in the stream, which can shade out ground plants, cause a reduction in primary productivity. It can even cause a reduction in dissolved oxygen, especially if it's in a settled open water system. There can be things that we can do to reduce erosion and leaching in agricultural systems. I would know this idea of terracing, so that allows for the terraces to kind of control water flow across the soil system, even if it's a highly elevated system. We can also use cover crops, so you can lay down, once you expose soil, you can lay down like hay or straw or something to protect that soil from being picked up and lifted away. In addition to, I think I said cover cropping, but what I meant to say is you can cover your soils, but you can also use additional rotational crops to protect soils if you're giving your soil a little bit of a rest. How does that protect the soil? Well, it protects against raindrop impact. It allows for greater infiltration of water, but the water is then, the water and the soil are both stabilized, reinforced by the soil roots, and it protects against erosion from surface water flow, and it's great way to protect soils. Here you can see a picture of a watershed. Why is a watershed important? A watershed is important to understand because we can look at a watershed and kind of make some predictions about what's going to happen downriver. So as you can see here in this watershed, you have all of these elevated areas, and all of the water that falls on these sides of the mountain are all going to percolate towards little creeks and streams that are going to go to major rivers, which are then going to flow out into major surface water systems. So everything that you do within this watershed is going to get picked up by that water and end up in those surface water systems. And that's why understanding watersheds is so important. It can also help us make some predictions about flooding, like if it's raining really hard on this mountain, we might have flooding downstream, and those sorts of conditions. In order to protect watersheds, we can use riparian buffer strips. Riparian buffer strips are where you plant trees and stuff in between agricultural land or land that you're managing in a way that could be detrimental downstream, and you have typically a series of trees and bushes and accumulating plants that either accumulate nutrients or pollutants pretty well. And so what ends up happening is that then keeps the water from getting that accumulation of nutrients, which then can cause things like harmful algal blooms and all of the things that we've talked about throughout the course of the year. When you're looking at the Earth's atmosphere in this picture, it makes you feel like the Earth's atmosphere is this really, really deep, deep thing. It is not. If the Earth was an apple, the atmosphere would really be just the skin of the apple. But when we're doing models like this, we make it look larger so that we can get more information into the model. The big key takeaways here that you need to know are the troposphere is where weather happens and where most atmospheric pollutants are going to interact with us, because that is the layer where weather happens and where we breathe. Okay? Then just between the troposphere and the stratosphere, or at the bottom part of the stratosphere, is the ozone layer. So we call that stratospheric ozone. Stratospheric ozone is very good because it protects the planet from UV radiation. The other things you just pretty much need to know that they exist. There's the thermosphere, which is actually really hot. So typically as you go up the layers of the atmosphere, things are going to get really cold, right? Because you're entering into space and there's nothing to trap that photic energy of the sun and keep things warm. However, in the thermosphere, it just so happens that it resonates with the ions that are there, or the sunlight resonates with the ions and it causes it to be really warm. So we call that the thermosphere, and then we have the exosphere on the outside. Mesosphere is in between. Weirdly, its name means. Right now we're going to be focusing on the troposphere because that's where weather occurs. We're going to be talking about how sunlight hits the equator right here on our planet with higher intensity than anywhere else, which is then going to cause the warm air to rise. As the warm air rises, it comes in contact with cooler layers of the atmosphere, or cooler parts of the atmosphere, which causes that water to condense and rain down right here, which is why you see this band of rainforest right here. That cell, called the Hadley cell, is then going to have that dry, cold air. Then it's going to come over here. Because the air is so dry, you're then going to see a band at about 30 degrees north and 30 degrees south of desert, right? So these are called weather cells. Because the cells are turning like this and the Earth is spinning in that direction, then it appears, right, as it's going like this, it appears that the wind is moving in that direction. And so trade winds have a tendency to look like they're heading in that direction. If you're looking head on to the planet, it's like kind of toward bottom and towards the left, right, into the southeast area. The seasons are also caused by the sun. So you can see that our planet is tilted a little bit. So it's not just straight up and down, it's tilted a little bit. And because of that tilt, in the summer, the northern hemisphere is facing directly towards the sun. In the winter, the northern hemisphere is going away from the sun. So this would be summer in the north and winter in the north, and then this would be winter in the south and summer in the south. So my husband's dad lives in New Zealand, and so when we did a summer trip down to New Zealand, we went skiing, right? And so here you're going to see the transition between winter and summer is going to be spring, and between summer and winter is going to be fall. So that's how the sun drives season. El Nino and La Nina are two weather phenomenons that you need to be aware of. What ends up happening is that the trade winds that are typically heading in this direction, like we just discussed, weaken for a variety of reasons. And because of that, the warm water that's usually pushed against Western Pacific Ocean, like Indonesia, New Zealand, and Australia, is going to then start to head in this direction. As that warm water and air shifts, you're going to have higher rainfall on this side, and you're going to have droughts on this side, right? So that's an El Nino event. In addition to that, you typically have a warmer winter in the United States. You need to know that. You're going to have fires, droughts in the United States, Indonesia, and Australia. This can cause increases in disease because oftentimes this area of South America doesn't have good sewage treatment systems, and so things like cholera and other bacteria transmitted diseases are going to get into drinking water. And in addition to that, it creates a set of conditions for vector organisms like mosquitoes and ticks that can carry disease. So you have increase of both flooding, monsoons, landslides, but you also have all of those parasites and disease. El Nino actually has a global impact, although we focus on the western side of South America and the eastern side of Australia and Indonesia. If you know just a little bit about what also happens in the United States, that in El Nino events, oftentimes we have warmer and drier years. The other thing that I forgot to mention previously is that when you have that accumulation of warm water on this coast, you don't have the upwelling of cold water, which leads to great fisheries in this part of the world. The antithesis of El Nino is La Nina. So in La Nina, it's when the weather pattern shifts again, so the trade winds are reestablished, but they're actually just a little bit stronger. So you have a harder push of more warm and more wet air against the Indo-Pacific and the Australia's eastern coast, which causes storms, disease, vector organisms, all of those sorts of things, including flooding and other associated issues. Over here in Ecuador and Peru, you can have droughts, and it has a tendency to have to lead to cold winters in the United States of America. So this summarizes the abiotic factors that you definitely need to be associated with, not including all of the components of the nutrient cycling, but the basic plate tectonics, weather, soil formation. I hope you've enjoyed the lecture.